Welcome everyone. So today is the third tutorial session in the subject dynamics of single degree of freedom. So did you go the week 2 and week 3 contents, and did you find anything which is a bit difficult to follow? Am I audible?
Yes, ma'am, you are audible.
Yeah. So, any particular suggestions where you found something difficult to follow, or otherwise we'll pick up the topics as like we'll do some uh, forced vibration under harmonic excitation, and then we'll take up periodic forces. So,
Ma'am, I was unable to go through the videos.
at least go through week 2 lectures.
No, many of them are remaining still.
Okay. Okay, let's start today's session, and let's see how much we can do. Okay. Just hang on for a second. Yeah. So start with response of undamped response of undamped systems under harmonic forces. So suppose there is no damping in the system, and this is the equation of motion, and it is subjected to a force P naught sine of omega t, and it is subjected to initial conditions u at uh, that is at t is equal to 0, u0 is u, and the velocity at t is equal to 0 is u dot. Now the solution of this equation, which I just wrote, equation number 1, it will have two parts. It will have a complementary part and particular part. Complementary part we have already solved it as a part of the free vibration problem. So let's do the forced vibration part. So for that it will have a particular solution, and let's assume that the particular solution is of the format. So mu dot plus ku will have a complementary solution as well as particular solution, and from knowledge of free vibration we know that a complementary solution is of the form a cos of omega nt plus b sine of omega n t. Now let the particular solution of this equation be okay, let's assume that it is of the form u p t is equal to c sine of omega t. So we have to find u p dot t is c omega cos omega t, u p t double dot is c omega square sine omega t with a negative sign. So if you substitute this in equation 1, you will get m u double dot is minus c omega square sine of omega t plus k c sine of omega t is p naught sine of omega t. So from here you can calculate the value of c. Sine omega t is there on the left hand side and right hand side, and it cannot be equal to 0, so you can easily remove it. So here you will have minus m omega square plus k is equal to p naught. So c is equal to p naught by k minus m omega square. Let's take k common from here. So you are left with 1 minus m omega square by k, and then you can write p naught by k 1 minus 1. What is omega n? Omega n is under root of k by n. So omega n square is equal to k by n, and let's use this fact in this equation. So this will be omega square, and m by k can be written as omega n square. So from here we get the value of c. So this value of c can be substituted back to this equation, and you get the particular solution. So the total solution is the summation of complementary and particular solution. So u of t will be the complementary solution, a cos of omega n t plus b sine of omega n t plus the particular solution, which is p naught by k 1 by omega n whole square. So this is their complete solution. Okay, I missed sine. This is c sine omega t. So this is your solution. Now let's use the initial conditions and calculate the value of a and b. So
Sine omega and t got cancelled. Sine omega t got cancelled.
oh, so this is the value of c, and your particular solution is c sine of omega t.
Okay,
So I
got it.
substitute the value of c, and sine omega t came from there.
Yes, okay.
Okay. Now we have to use this fact. Let's use the initial conditions. So at t is equal to 0, u is u0, cos 0 is 1, so a, sine 0 is 0, so this goes away, and at t is equal to 0, sine omega t is also 0. So the value of a is calculated. Now you have to write u dot t. So that will be a omega n sine omega n t with a negative sign plus b omega n cos omega n t plus p naught by k 1 by omega by omega n whole square cos omega t with omega. Okay. Now at t is equal to 0, u dot 0 is u0, this first term goes away. You will have d omega n plus p naught by k 1 by omega n whole square times omega. So from here you can calculate the value of d. So d will be u naught 0 by omega n minus p naught by k 1 by 1 minus omega by omega n whole square omega by omega n. Right, that is in like here I divided by omega n throughout, and then I moved this second term to the left hand side. So this is how I get the value of a and b, and then I can substitute the value of a and b back to this equation, and that will be my complete solution. So what do I get? U of t is equal to a is u0 cos of omega n t plus d is this term u dot 0 by omega n minus p naught by k 1 by omega n whole square omega by omega n. This entire term is b sine of omega n t plus the particular solution, which is p naught by k 1 by omega n whole square into sine of omega t. Now what happens here? The first two terms are a function of, you can see it's a function of omega n, and the second term it's a function of omega, and I'll just explain you why this is known as steady state and why the first two terms are known as the transient. You will be able to better appreciate it when we go for the damped vibration. This is undamped. So what happens, like if I plot my force, that is P versus T, will be something like this, where the amplitude of the force is P naught. I'm talking about the force which I'm applying, that is the force which I'm applying on the system is P naught sine of omega t. So the force will look something like this, where the time period is 2 pi by omega. This is how we define time period. Now if I plot here, I have normalized the time axis with the respect of time period, and suppose here u of t is also normalized with certain quantity. Let's say these are normalized axis. Here what do we see? That my steady state response, this being the steady state component, that is governed by omega, it will be what I mean to say, it will have a period of omega, same as that of the exciting force. And because of this transient response, your total response will be something like this. Because of this transient response, it will have a harmonic quantity added with it, which has a frequency of omega n, and this will be the total response. And had it been a damped case, then the effect of this omega n will die out, as we'll see, and slowly your solution will approach the solution of the steady state one. This effect of omega n will die out. Here it won't die out because we are considering an undamped case, which is purely an academic exercise. So this blue one is the total response, and this dotted line is the steady state response. So let's consider in this solution which we had written. In this solution which we had written, that your initial conditions are 0. Initial conditions are 0, meaning here u of 0 is 0 and here u dot 0 is also 0. So your u of t will become, now u of 0 is 0, so the first term goes away. U dot 0 is equal to 0, then this term goes away, so you are left with minus p naught by k, 1 by 1 minus omega by omega n whole square. Then you will have omega by omega n sine of omega n t plus p naught by k, 1 by 1 minus omega by omega n whole square sine of omega t. Now here if I take p naught by k, 1 minus omega by omega n whole square common, I am left with sine of omega t minus omega by omega n sine of omega n t, right? So here this is the steady part and this is the transient part. So even if the initial conditions are 0, you will have a transient part and a steady state part. Okay, now let's write it. Now let's take up the steady state part of the solution, and because like finally the transient part will die away, not here but in the damped case. So just pick up the steady state dynamic response. We'll be doing certain manipulations with that. So u of t is equal to p naught by k, 1 minus omega by omega n whole square sine of omega t and we can say that, see, a force of p naught into sine of omega t, that is the force acting on the system. Now suppose we are ignoring the dynamic effects in the system, that is no initial force is acting. If no initial force is acting, then we can use the concept of kx into f, k times x is equal to f, so deformation is f by k. So if we use the same concept here, ust as a function of time will be p naught by k sine of omega t, and maximum value of this is when sine omega t turns out to be 1. So ust naught is equal to p naught by k. That is, we can write that u of t is ust naught 1 by omega n whole square sine of omega t. Now, or instead of writing it like this, we can what we can do that we can write this equation. Yes, any problem?
Ma'am, I did not understand how we came from U of t to UST of t.
Just a concept, like you can think like for the sake of convenience I'm writing it like this. Can we write this k of x is equal to f, or when is this valid? This is valid when we don't consider inertial effects in our system. This equation of motion mu double dot plus ku is equal to f. Suppose I don't consider inertial effects in the system, then this will go to zero. Inertial effects, that is force which is developed due to inertia. So the same thing I'm writing here, that k is equal to f by k. Here what is the force acting on the system? The force acting on the system is p naught sine of omega t. That the force acting on the system is p naught sine of omega t divided by the stiffness is k. And let's say this, I give a name USTT. This is a nomenclature which I'm using to write my equation. Now this USTT, when does it take up its maximum value? When sine omega t goes to 1. So UST naught, the peak value when sine omega t is 1, you can write UST naught is equal to P naught by K, right? And when similarly what will be the peak value of this quantity? I can write it, let's use the notation U naught. U naught will be P naught by K 1 by omega n whole square. That is when sine omega t is equal to 1, right? Is this clear?
Yes, ma'am.
I'm just telling when these quantities will take up its maximum value. And here I am introducing a term RD, which is RD, which is the deformation response factor. I define RD to be equal to U naught divided by UST naught. So what is U naught? U naught is P naught by K 1 by 1 minus omega by omega n whole square, and UST naught is P naught by K. So D is 1 minus omega by omega n whole square. So how did I get it? Last week we also discussed one more content, that U of t can be written in the form of U naught sine of omega t minus phi. This is by using the trigonometric identities. By using trigonometric identities, you can move those quantities. We learned it with respect to solution of homogeneous equations, that if we have sine and cos inside the brackets, you can just move them out and you introduce the angle of phase angle, similar to that what we do in SHM as well. So here phi is the phase angle. So like we with this notation, like we know u of t is p naught yk. So p naught yk we just wrote it is equal to ust naught, ust naught. So this multiplied by you have or you can also think in this manner that u naught is rd into ust naught. So rd into u ust naught into sine of omega t minus phi. And it is seen that when this is the definition of RT. So when you plot RD, that is the deformation response factor, with respect to the omega by omega n ratio, this is the definition of RD. When the value is, when omega is equal to omega n, that is when this ratio omega by omega n is equal to 1. It is undefined. When omega by omega n is 0, it is 1. So on this side of on the left hand side, the graph is like this. And when, let's say, omega by omega n is a very large number, then it will approach 0. And when your omega by omega n is just greater than 1, then also it is infinity. So on this side your plot is something like this, right? And for phase angle, when phi is equal to 0, when omega is less than omega n, and it is equal to 180 degree when omega is greater than omega n, right? And then I can plot it here as well. So I'll just show you now. One important thing, whatever solution we discussed here, this solution, it is applicable only when omega is not equal to omega n, that is when there is no resonance. Suppose there is resonance, then this particular solution will change. So for that case, the solution of the particular solution will change. So let's assume, so if omega is equal to omega n, then your
And
particular,
the axis on the second graph are same as the one above?
yeah, this is omega by omega n, and this is the phi.
Okay.
So this is 0 degree and this is 180. Okay. So your particular solution is of the form Ct cos of omega nt. Now in the similar way, you have to calculate the value of C. So upt dot is C. So you will have to use t, then omega n sine omega n t plus cos omega n t, and ut double dot sine of omega n t. So t, differentiate sine omega n t, so omega n cos omega n t plus sine omega n t, differentiation of t is t minus omega n sine omega n t. Now substitute it back into the equation, mu double dot plus ku is equal to p naught sine of omega nt. U is p naught by k sine of now let's write omega t. Finally omega is equal to omega n because this is resonance. Then the differentiation correct? Can you please check? Step correct. Step number 1. Here I'm using that formula. UV differentiation of UV is U into V dot plus V into U dot.
Yes, ma'am. First step looks okay.
Then can you check the second one? Minus omega n square t cos of omega n t minus omega n sine of omega n t minus omega t plus k by m is omega n square. U is c t cos of omega n t plus p naught by k sine of omega n t. This term and this term goes away, so you're left with minus 2c omega n sine of omega n t p naught by k sine of omega n t. So your c is of the format minus p naught by 2k omega n. Okay, so this is how you can calculate c. Is this clear? I'm just manipulating the like solving the equation. So your u of t will be the complementary solution a cos of omega n t plus b sine of omega n t minus c into this particular solution, c into t into cos of omega n t. Now again you can calculate, use the initial conditions, that is u at t is equal to 0, u0 is u and u dot is equal to the velocity at u at t is equal to 0, your velocity is u dot. So if you use it here, you can calculate that the value of a, and again you can calculate the value of b. For that u dot is equal to minus omega n a sine of omega n t plus differentiation of b sine of omega n t is b omega n sine of omega n t minus
Cos.
Cos cos of omega nt minus p naught by 2k omega n. So you have two terms. So if I take up differentiate t, so omega nt plus t is remaining, so omega nt minus omega n. So u dot 0 will be, the first term goes away. Here you are left with b omega n minus p naught by 2k omega n. Cos omega nt is 1 minus, again you have a t multiplied, so that goes away. So throughout, if I divide by omega n, so b will be equal to u dot 0 by omega n plus p naught by 2k. So this is how you get the particular solution when it's a case of resonance. So if I write down my complete solution, u of t is u0. I'm rewriting this equation. Cos of omega nt p is u naught 0 by omega n plus p naught by 2k sine of omega nt minus p naught by 2k omega nt cos of omega nt. Now let's assume that the initial conditions are 0, that is u0 is equal to 0 and u dot 0 is also equal to 0. Then what will happen to u of t? U of t will be equal to, this first term will go to 0, this will go to 0. So you are left with p naught by 2k sine of omega nt minus p naught by 2k omega nt cos of omega nt. So I can write this as minus 1 by 2 p naught by k, okay, omega nt cos of omega nt minus sine of omega nt, right? So, or in other words, have a t term multiplied here, that is, as time increases your response will go on increasing. Let me write it in other format. We just told that ust naught can be written as p naught by k. Let's use this fact and let's write, instead of omega n, let me write it as 2 pi by tn, just to manipulate the equation. So u of t can be written as, you have that minus 1 by 2, p naught by k can be written as ust naught. Let me bring this ust naught on this side. Finally, when I'll show you some figures, I will have this in ratio, that is why I brought it here. Then I have the term omega n, which is 2 pi by tn into t Then you have cos of omega n, which is 2 pi by Tn into T, minus sine of omega n is 2 pi by Tn into T. So when you plot this, you will see that on this axis, on the x-axis, you have T by Tn, that is this number, and on the y-axis you have this ut by ust naught, and you will see that your response will go on in, and suppose, yeah, it will go on increasing like this. Now this is one more thing which you can observe, that the difference adjacent peaks is pi terms away. How can I derive that? Remember, now I want to derive this. This is your solution. It will grow on time. Just remember, this is a very it's an academic example. You will always have damping in the system. You don't have any damping in the system, and your a resonance condition is reached when omega is equal to omega n. Then situation like this happens where the response keeps on growing. Suppose I want to know that like when I move from one cycle to another cycle, that is, let's say this is uj and this is uj plus 1, how much is the increase in the amplitude? So suppose I use this equation, j by ust naught is minus 1 by 2, so 2 pi by Tn. Let's say at uj the time is t, cos of 2 pi by Tn t minus sine of 2 pi by Tn into t at time period Tn apart, uj plus 1 ust naught is equal to minus 1 by 2, so you will have 2 pi by Tn. Your time period is t plus Tn. Cos of instead of t, if you write t plus Tn, it will have the same period, so you will have the same term t, and here you will also, since the period is same, so you will have same terms here. Now let's subtract them. uj plus 1 minus uj, the difference, now you have minus half, so 2 pi by Tnt plus 2 pi, the entire thing multiplied with cos of 2 pi Tnt minus, you have sine of 2 pi by Tn into t. Then you have minus this quantity, so if I take minus half common, so you will have 2 pi by Tn into t cos of 2 pi by, I'm subtracting this, so minus this plus of sine of 2 pi by Tn into t. So this term and this term goes away. this term and this term goes away, so basically you're left with minus half into 2 pi cos of 2 pi by Tn into T, like something like this. And here I'm talking about amplitude, so this term is actually reaching 1. So the difference between the peaks will be this term, difference between the peaks will be minus pi. So that is why I have written here minus pi. So if you think in terms of ratio, the ratio of the amplitude at uj plus 1 divided by uj is pi, or in other words, if I don't think in terms of normalized coordinates, the difference between these two will be pi into ust naught. And what is ust naught? It is equal to p naught by k. So we'll be
Yes, ma'am.
solving, yeah, we'll be solving some questions as well. So let's do the same thing when there is viscous damping. So harmonic vibrations with viscous damping. So your equation of motion is mu double dot plus cu dot plus pu is equal to p naught sine of omega t. Again, you have a set of initial conditions that at t is equal to 0 your velocity is u, and at t is equal to at u is equal to 0 your displacement is u and your velocity is u dot. So again, you will have a pair of complementary solution and particular solution. So here your particular solution is of the form c sine of omega t plus d cos of omega t. This is the form which you are assuming. Then how do you solve it? So you take up this equation, and let's say I am dividing it throughout by m. So c by m u dot plus, this should be k. So k by m times u is equal to p naught by k sine of omega t. Or I can write this as u double dot c by m is 2 zeta omega n u naught, k by n is omega n square times u, so p naught by k sine of omega t. And your particular solution is of the form c sine of omega t plus d cos of omega t. So just take the derivatives and substitute it in this equation. So e dot is c omega cos of omega t minus d omega sine of omega t. This is the first derivative, and your second derivative is c omega square sine of omega t with the minus sign minus d omega square cos of omega t. Now substitute these in this equation. So you will have minus c omega square sine of omega t minus d omega square cos of omega t plus 2 zeta omega n. U dot is C omega cos of omega t minus d omega sin of omega t plus omega n square. U is again C sin of omega t plus d cos of omega t is equal to P naught by K sin of omega t. Then in this equation, collect all the coefficients of the term sin omega t and all the coefficients of the term cos omega and cos omega t, and then you can equate the terms on the left hand side and right hand side. So if I want to collect the coefficients of the term sin omega and t, you will have this first term minus c omega square. Now let's do for cos omega t simultaneously. So cos omega t coefficient is minus d omega square. Now again cos omega t coefficient is 2 zeta omega n c omega, and here you have minus 2 zeta omega n d omega, that is I'm writing this term. Then we have this term, let's consider this term. So here the coefficient is c omega n square, and for cos omega t the coefficient is d multiplied by omega n square, so plus d omega n square. Now this is equal to P naught by K sin of omega t. Now on the left hand side the coefficient of sin omega t is this, and on the right hand side the coefficient is this, and on the right hand side cos omega t has a coefficient 0, and on the left hand side you have a coefficient this. So you have two unknowns c and d, and you have two equations. So using these two equations you can calculate c and d. So let's write down the two equations. So your first equation is n square minus c omega square minus 2 zeta omega n d omega is equal to P naught by K. So I can take out c common, and I can divide the equation throughout by omega n square. So c times 1 minus omega by omega n whole square minus 2 zeta omega by omega n times d is equal to P naught by K. So this is my first equation, and my next equation, this comes from coefficient of sin omega t, and then equate the coefficient of cos omega t. There we can write d omega n square minus d omega square plus 2 zeta omega n square should be 2 zeta omega into c omega. C omega, this is equal to 0. So again I'll divide by omega n square. So this equation will be 2 zeta omega by omega n multiplied by c plus 1 minus omega by omega n whole square times d is equal to 0. So if you solve these two equations, you will get the value of C and D. And these were the values of C and D. You might have seen them in the lectures as well. So C comes out to be P naught by K 1 minus omega by omega n whole square by 1 minus omega by omega n whole square of this plus 2 zeta omega by omega n whole square. This is the value of C, and D comes out to be P naught by K minus 2 zeta omega by omega n by 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So this is how we figured out the complementary solution. And when we had studied for free vibration, we had derived that the complementary solution is of the form. Is this particular solution clear? Since the answers were directly given in the class, I thought of explaining it, like how C and D
Yes.
is derived. Yeah. So your complementary solution is of the form minus zeta omega n t a cos of omega dt plus b sine of omega dt, where omega d is omega n under root of 1 minus zeta square. So your complete solution is of the form, you have complementary solution plus particular solution. So complementary solution is this part, a cos of omega dt plus b sine of omega dt, plus you will have a steady state part, which is, first you will have a complementary part plus a particular part, where this part will be the transient part and this is the steady state part. Steady state, and this is the transient. Like if I plot t versus small t versus capital T here, normalized axis, even this is the normalized axis, your total response will have the period, will have the frequency omega coming into picture. You will have the, because of the transient part, you will have this omega n coming into picture, but slowly it will die out and eventually you will be left only with the steady state solution. So this total line, solid line, is the total response, and the dotted line is the steady state response. Again, the solution which we just discussed, it has terms like omega by omega n, right? Okay, so we found out the solution. Now Let's see what happens at resonance, because in case of undamped case we found that at resonance we had to calculate a different solution, we had a different particular solution. Why did we had to calculate, why did we do it? Because the particular solution which we found, there the constant, yeah, there our constant was of the form this, where if omega is equal to omega n, c will go to infinity and we can't use this solution. But in case of a damped solution, our solution is of c and d is of this format. When omega is equal to omega n, this term goes to 0, but we still have these terms, so we can still use this solution. So when omega is equal to omega n, we will see what happens to this solution, right? If we substitute omega is equal to omega n, omega is equal to omega n, c will be equal to 0, because the numerator, in the numerator we have 1 minus omega by omega n whole square. What will happen to d? D will have, in you have p naught by k from here, then you will have minus 2 zeta, omega by omega n is 1, and again in the denominator you will have 2 zeta omega by omega n whole square, so you will have minus 2 zeta whole square. So this and this goes away, so you are left with minus p naught by k, I can write as ust naught by 2 zeta. And let's say for 0 initial conditions, so what in this solution, at resonance I know the value of c, I know the value of d, I don't know the value of a and b. Now I am telling, let's say my initial conditions are 0. If my initial conditions are 0, we just saw that you can calculate the value of a and b. That is what I want to tell is, let's say my u of t is of the form e to the power minus zeta omega n t a cos of omega dt plus b sine of omega dt. Now omega is equal to omega n. C is 0, let's use it, and d is equal to this quantity minus ust naught by 2 zeta sine of omega t. Right. Now let's calculate a and b. For that I want you to use the fact that, let's say u0 at t is equal to 0, let the displacement be u and let this be equal to 0, and u dot, this is also equal to 0. So with this fact, if you can solve it here, I'm skipping this. Okay, let's try to do this. 0 is equal to t of anything to the power 0 is 1, like e to the power 0 is 1, then you are left with a p becomes 0. Here you have ust naught by 2 zeta sine omega nt, so this is 0. Did I do anything wrong? Is this equation fine? I substituted and I found out the value of d. I substituted it here. Now I want to calculate the value of a and b using zero initial conditions. Let at t is equal to 0, let the velocity be u, let the displacement be u. So u0 is, okay, here is the problem. Your particular solution was of the format c sine of omega t plus d cos of omega t. So when I'm writing it here, it should be c sine of omega t plus d cos of omega t. So here when I write it here I'm substituting the value of d, which is minus ust naught by 2 zeta into cos of omega t. Then when I'm substituting it back, when I'm calculating the coefficients a and b, I get a minus ust naught by 2 zeta cos omega t is 1. Let's say this is equal to 0. So from here a is equal to ust naught by 2 zeta, right? Then I want to calculate the value of b as well. So u dot t is equal to e to the power minus zeta omega nt. This will be a omega t sine omega dt minus plus b omega d cos of omega dt minus ust naught by 2 zeta into omega sine omega dt with a plus sign. Now I have other terms as well. A cos of omega dt plus b sine of omega dt, derivative of e to the power minus zeta omega nt is minus zeta omega nt into e to the power power minus zeta omega n t. When you solve this, you will get b to be equal to ust naught by 2. Under root of 1 minus, sorry, you will get a term like this, and then you can write down the equation for u of t. Here I want to okay, let's just confirm this as well. So at t is equal to 0, let this velocity be u dot minus a omega t. So this sine of omega t at t is equal to 0 is 0, plus b omega d. So this becomes 1, plus sine omega t is again 0. Then here you have a cos, this term goes to 0, minus zeta omega n. Suppose this is equal to 0. A is ust naught by 2 zeta minus zeta into omega n. So let's divide by omega d throughout. So from here b is equal to omega n by omega d minus ust naught by 2 zeta omega d. D is omega n 1 minus zeta square. So zeta omega n by omega d is 1 minus under root of 1 minus zeta square minus ust naught minus 2 zeta. Can you check where I'm making a mistake? I should be getting something. This, can someone confirm whether this derivative is correct or not? Okay, we can do a thing. We can quickly take a break of 5 minutes. In the time being, you can check this equation. I want you to check whether this derivative is correct or not, and then we'll resume our class. So please check this equation. Did anyone try checking the derivative? So I'll just mention what should be the value of b which you should be getting. I'll try to derive it and put it in the notes. For the time being, I'll just mention what is the value of b which you should be getting. So the value of b you should be getting is UST naught by 2. This is the value of b which you should be getting, and finally your u of t will be of the format UST naught by 1 by 2 zeta e to the power minus zeta omega nt cos of omega dt plus zeta by under root of 1 minus zeta square sine of omega dt minus cos of omega nt. Now let's say for a certain value of damping, let's say 5%, you plot the response. That is, here I have u of t by UST naught. And on this axis, suppose you have t by Tn and 0. And here it is observed that your response will lie between these two lines. This is the steady state amplitude, and this line is the envelope curve, and it is seen that and what will be your bounding value, that is when t becomes large here. You can see it from this equation itself, that is at the bounding
1 by 2 zeta.
Yeah, so this is what you will reach. So this can be used for calculating the damping present in the system. I will just show you an example. Now we just studied the response reduction factor for undamped system. Similarly, we can study the response reduction factor for the damped system as well. where you will be using this equation. This equation which we just read, we took this equation and we calculated the equation for u. So you can use this equation, the one which I marked, this. Using this equation, you can write u of t in this format as well. You can write u of t is equal to u naught. What did you have? U of t was equal to e to the power minus zeta omega n t a cos of omega t t plus b sine of omega dt plus c sine of omega t plus d cos of omega t. Now I can use arithmetic trigonometric quantities and like equations, and I can combine it to write u of t will be something of the format u naught sine of omega t minus phi. And again, how we had defined rd, we had defined rd to be u naught by ust naught. This is what we had derived like defined earlier. So here again I will write u naught to be rd into ust naught into sine of omega t minus phi. Where how do I calculate this u naught? Here your u naught will be of the form, again here I am picking when I am writing this equation, let's assume there is no transient part of the solution. You are picking up only the steady state part of the solution. So this is the steady state part of the solution. C cos of omega t plus d sine of omega d, c sine of omega t plus d cos of omega t. So here u naught will be of the form c square plus d square, and what will be tan phi? Tan phi will be minus d by c. So from here you can calculate the value of r. So your rd is u naught by ust naught. So if you can substitute u is equal to under root of c square plus d square, and we just wrote down the two equations for calculating c and d, and we also calculated the value of c and d. So if you substitute everything, the equation which you will get is of the format 1 minus under root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. This is how you calculate the value of rd, and phi will be tan inverse of, substitute the value of d and c, you will get 2 zeta omega by omega n by 1 minus omega by omega n whole square. So you just have to calculate the equations properly and you need to substitute it. So you can do one question that suppose the displacement amplitude u naught of a single degree of freedom system. Let's do a small question. The displacement amplitude u naught of a single degree of freedom system due to a harmonic force. It is known for two excitation frequencies. It is known that when omega is equal to omega n, your u naught is equal to 5 inches, and when your omega is equal to 5 omega n, your u naught is equal to 0.02 inch. I want you to estimate the damping ratio of the system. Estimate the damping ratio of the system. So maybe we can pause for 2 minutes, think about the question, and then we'll solve it. Okay, so this equation for Rd, when omega is equal to omega n, what will happen to your Rd? It will be, yeah, right? Now, what is Rd? Rd is u naught by ust naught, right? And what is given in the question? It is given that u naught is nothing but the displacement amplitude. Displacement amplitude is given. Now you know that the displacement amplitude is 5. ust naught is not known. So from here you have one equation that ust naught by 2 zeta is equal to 5. Now again you know that when omega is equal to 5 omega n, u naught has a certain value. Now when omega is equal to 5 omega n means what? Can you omega by omega n, omega is equal to 5 omega n means this ratio is much more than 1. If it is much more than 1, what will happen? This equation of Rd, 1 minus omega by omega n whole square, you have a square of that, means here you are getting a 4th order polynomial, plus 2 zeta omega by omega n whole square under root. So when omega by omega n is much greater than 1, when omega by omega n is much greater than 1, here you will get a 4th order polynomial, and that will be the it will be the controlling term. So approximately I can drop the other terms and I can write your 4th order term will be omega by omega n whole to the power 4 under root of that. So you will have a square term like this. So your RD is U naught by UST naught, and that is equal to, with the approximation, omega, it is omega n square by omega square, or in other words, your U naught is equal to UST naught omega n square plus omega square. Here let's use this. Your UST, when this is the case, your when omega is equal to 5 omega n, your U naught is 0.02 inch, right? So this is 0.02. How much is your UST naught? Your UST naught is 5 into 2 zeta. And what is the ratio of omega by omega n? Omega n by omega, it is 1 by 5. So substitute it here. So from here, can you calculate the value of zeta? Your zeta will be equal to 5.
0.05, yes.
So is this manipulation of RD clear? Here
The
I'm writing,
approximation of RDS.
yeah,
Yeah.
the way we did this. So from here, like if you see the plot of RD versus frequency, if I'm talking about this expression, if you plot this RD against omega by omega n, and let's say your damping ratio is also varying, it is seen that you have omega by omega n on this axis, then you have RD on this axis. So when omega by omega n is equal to 0, when the omega by omega n is equal to 0, your RD is 1. So you start from here, right? When suppose your damping ratio is a very small number, so your response will be same. When it is 0, we just saw it will have a, here the value is 0, it will be something like this. As damping goes on increasing, your response will be something like this. Like since I'm drawing by hand, it's a very schematic sketch. And then but it's seen that when damping is equal to 1, your entire response is less than 1. You can say that like in comparison to static deflection, because how do you define RD? RD is U naught by UST naught. UST naught is when you consider the force to be static. Your response will be much your response will be lesser than that of the static case. So this is when your damping is 1, and here when your damping is, let's say, 0.01, and like as you increase damping, your response will go on decreasing like this. So this is how this response reduction deformation response factor is used. Then we had already discussed this half power bandwidth method last class, so I'm not repeating it. Okay, last class we had derived the the transmissibility ratio when a force P naught sine of omega t is acting on the object, and I had told that suppose if there is a ground motion, then the transmissibility expression remains the same, but we had not derived it, so let's derive that. So just for the sake of recap, this is what we had seen, that suppose the body, you have a force P of t acting on it, there is a spring and you have a damper like attached to it, and this is the force F of t. Now this force F of t will be the spring force plus damping force. Now spring force is k u as a function of time plus c u dot, and we had done the entire math and we had found out that this F of t is nothing but, suppose k u of t can be written as ust naught, what we were just writing here. What is u of t is ust naught into rd into sine of omega t minus 5. So here I am taking u to be written like this, rd into ust naught into sine of omega t minus 5, and I'm substituting this u in this equation. So yeah, rd ust naught sine of omega t minus 5 times k plus c into u naught will be again rd ust naught omega cos of omega t minus 5. Now suppose what will be the maximum value of f of t? Let that be f of t naught. It will be ust naught, this ust naught is common, rd is like we can remove common, and here the amplitude is k and here c into omega. So how we uh, how we wrote here, I'll just draw an analogy so it will become clear. Yeah, see how we wrote here, u naught is equal to under root of c square plus d square. If the particular solution is here, we use some trigonometric formula. Here also, here the what will be the amplitude? It will be k square plus c square omega square, right? So now if I want to divide, now ust naught is p naught by k. Suppose I'm substituting it here, ust naught is p naught by k, and I bring the p naught on this side, so rd, and suppose I have a k left, I move it inside. I have 1 plus c square by omega square by k square. Now this is under root of 1 plus k square by omega n is under root of k by m, so omega n square is k by n. So and I have zeta is equal to c by 2m omega n. So I can write this as I want c square omega square by k square. In case of c square, I want to write zeta square for m square omega n square from this equation into omega square, and k square I'm writing as omega n square into omega k square from this equation will be omega n to the power 4 into m square. So omega n to the power 4 into m square. So this will be 4 into zeta square omega n square. M square and m square goes away, and this square, and you're left with omega n square. So if you can substitute this here, you will write 2 zeta omega by omega n whole square. Now this is, you already have an expression for RD. Here we had derived, this is your expression for RD. So here if you substitute this expression for RD, you will get f t naught by p naught. You have this in the numerator, 1 plus 2 zeta omega by omega n whole square by 1 minus omega by omega n. Simply I'm substituting RD from here, 1 minus omega by omega n whole square plus 2 zeta omega by omega n square of that, and I have a root as well. So this is nothing but transmissibility. This is what we had derived. Now what I want to do, instead of applying a force on the body, suppose I have a mass m, I have a spring K, a damper C, and suppose my ground itself is moving. Suppose this is UG, and let this be U total, and let this UG, let the ground acceleration be of the format UG double dot sine of omega t. Right. Now your U of t, here we had written U of t to be of the format UST naught into RD sine of omega t minus phi. I'm writing this from here, right? Now here we know that when there is ground acceleration, what is your P effective? P effective will be minus m into UG double dot. This we had done in the last class. So here I can write your P effective will be minus m UG double dot from here. UST naught is that force divided by K. So that divided by K into RD sine of omega t minus phi. So in that way I can write U of t. Now what is this U total? U total will be ground acceleration plus the relative total displacement will be ground displacement plus the relative displacement. So I can take dot, means the velocity will also follow the same relation, as well as the acceleration will also follow the same relation, right? Then what I am doing is what I want to do is I can take suppose I have this expression of u of t. Now I can here I can substitute this here. Now I have an expression of u of t. I can take the double derivative and I can substitute it here. So this will give me an expression for u total, the double derivative of u total, that is the total acceleration of the body. And if I here in this case your transmissibility will be how much, because of this ground acceleration or ground movement, how much acceleration is transferred to the body. So here you will define transmissibility by u naught double dot t, not I'm putting because it is for the peak value, by u ground double dot. So if you do the maths, you will get the same expression. So let's derive this now. Doing is now what I want is, suppose u of t is minus m ug double dot by k r d sine of omega t minus phi. Let me, so how was this equation, how was this RD derived? As you can remember, this RD was derived by picking up this particular solution, that u of t is c sine of omega t plus d cos of omega t, and where c and d were calculated using these expression. Let's use this expression and write down the solution. So u particular we had seen, it is equal to c sine of omega t plus d cos of omega t, where c is p naught by k, 1 minus omega by omega n whole square by 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, and d is equal to p naught by k minus 2 zeta omega by omega n by 1 minus omega by omega n whole square. You have a square over this as well. 2 zeta omega by omega n. Now here what we had seen, your P naught, since this is a ground excitation, your P naught is equal to minus mug not double dot. This we had through force equilibrium, through like we had understood this by like we had subjected a body to ground excitation, and we had derived that your effective force becomes minus m times ug double dot. So if we substitute this value of P naught in this expression and this expression, and you will see that your u of t will be of the form P naught by K. P naught by K, if I substitute, it will be minus m ug ground double dot by K, and you will have 1 minus omega by omega n whole square, no change in this, plus 1 minus omega by omega n square of that, plus 2 zeta omega by omega n square. Multiply this by sine of omega t, since you have a sine omega t here. Basically I am substituting the value of C. Then plus substitute the value of D, which is minus 2 zeta omega by omega n. Then you have the cos omega n t term, cos omega t, and you have the same denominator like this. Okay. Now this is the value of u of t. Now if you have to calculate, you have to differentiate this twice, right? And then you have to substitute in this equation, and u g double dot, this you already know, this is equal to u ground double dot sine of omega t. So suppose I want to differentiate this, so this I can write as minus m u g double dot by k. Now if you differentiate it, it will be of the format u double dot t, is you will have this ground acceleration term, plus c1 sine of omega t plus d1 cos of omega t, where c1 and c2, I will give you the forms of c1 and c2. For this you can use some symbolic tools like available on internet, or you can use MATLAB to carry out the differentiation, or you can do by hand, whatever is convenient for you. C1 is minus 1 by omega n whole square plus 4 zeta square omega by omega n whole square, whole divided by 1 minus omega by omega n plus 2 zeta omega by omega n whole square, and d1 is equal to minus 2 zeta omega by omega n whole cube by 1 minus omega by omega n square of that quantity plus 2 zeta omega by omega n whole square. So what will be your amplitude of this expression? Amplitude will again be ug ground under root of c1 square plus d1 square. If you substitute c1 square and d1 square, and if you calculate this ratio, this transmissibility ratio, where TR is equal to U naught double dot G by U ground double dot, which is simply C1 square plus D1 square, and if you substitute it with C1 and D1, it will be equal to 1 plus 2 zeta omega by omega n whole square by 1 minus omega by omega n square of that plus 2 zeta omega by omega n whole square under root of that, which is same to this expression which we had obtained earlier. So the expression for force transmissibility is same as that of transmissibility when the base is moving. So this shows that the
So, ma'am,
yeah.
in transmissibility, if we provide an acceleration, if we provide a ground acceleration, what uh, what acceleration it will transfer to the spring mass system? Is
Yeah,
it transmissibility? Is it the definition of transmissibility?
how much is the body accelerating?
System,
Because
spring mass system,
spring
complete.
mass, yeah, how much is the spring mass system moving? And if you want to write this in terms of displacement of the body, the expression remains the same, that is U naught T by U ground, that is the same expression
Yes.
in terms of displacement. Then also this expression remains the same, that is this remains the same. So
Okay.
these are, like, today I thought of going through all the derivations. Without the derivations, doing the are becoming a problem. Next week we'll focus purely on questions, and then, like, extending it to periodic forces will be a bit easier, because periodic force is nothing but a combination of harmonic forces like sine and cosine. There you can directly you're directly extending the solution for this equation, which we did. Harmonic force with viscous damping, we established the solution for P naught sine of cos omega t. You are directly extending this solution,
Okay.
this one. So
Yes.
if you have any doubt, you might ask, or any particular thing which you want me to highlight in the next class. So anything do you want to specify?
Ma'am, next class, I request you to please solve as many problems so that we can prepare for
Yeah,
the
yeah,
term
yeah,
exam.
yeah. Next class will be purely problems. And one more thing, what I wanted to highlight is, like, if you understand the derivation, you don't need to remember
Yes, yes, ma'am.
them.
Yes.
Otherwise, like in the slides, if you directly see those
Yes.
equation, it becomes a little
Yes, so many
difficult.
things it
Yeah,
clears while going into the derivation part.
yeah, yeah.
It's really helpful. Thank you.
Next class, surely we'll be focusing 100% on problems.
Okay, ma'am.
Okay, okay. Thank you for
Okay.
attending the
Thank you, ma'am.
session.
Thank you.
Okay, okay. I'll